Okay.
Test demand is not the parameter interest, but it is an optimization assumption. It identifies,
Okay, again, we're,
so yeah, so you have parameter interest, which is y sub 1 minus y 0. That is identified by machine time under randomization. So you're identifying the parameter.
all right, I'm going to go ahead and get started. So again, this is really the same estimator applied to a different parameter. So the IPTW estimator, but now looking at a parameter that gets a lot of attention in publications. It's used quite a bit, called the Marshall structural models. And the most important word here really is we've been comparing two levels of treatment. No, there's no model required. Two numbers will describe any other. You just have two numbers and you can connect them with a line, but it doesn't really help you to simplify the summary of the relationship of y to the treatment. So this is where you really have more than one level of treatment, and you don't want to just get an estimate of the mean for every value of the treatment, but you want to connect them in some ways via a model, a line or a curve or something like that. So again, it's estimation. Working as MSMs, we'll start with just looking at including A, but once you have an MSM, you can also include the other covariates. So you can look at the effect within a subset of the W's, whether you could look at the effect within as a function of age, or look at the effect as a function of gender, whatever happens to be. And then we'll talk somewhat about inference for these estimators at the end. It's really, as I say, you can use the estimators we'll talk about it when you're just fitting an average treatment effect and using them. They just reduce to what we've already said. So the additional ideas here are only really useful when either A has many levels or a combination of A and some other covariate for which you want to look at the effect within. So it's a subgroup effect you want to look in, has many possible levels. We can look at blood pressure as a function of drug dose, not when it has just high and low, but it could have a sequence of ordered values, right? Again, our A is still going to be discrete at this point. There is no estimator equivalent to this for an A that's truly continuous. That's an ongoing research issue. So this still, in the end, you have to have several people that have 0 and 1 and 2, et cetera. It has to be discrete at some level, okay? So we want to define a target parameter that is a function not of each one of these levels separately, but all together. So option 1, though, is just to do comparisons like this. I often end up doing this, by the way, in practice, because I like to avoid assuming a model if I can, first thing. So I just simply look at the mean value, estimate the mean value of the outcome if you have the highest level, the next highest level down. I can plot those, and I can see, does it look like a line or not, right? I mean, to start with a line seems a little bit hasty to me. However, it could be a nice summary if, in fact, you have more than just 5 levels. But anyway, once you get more than 2 levels, doesn't mean you have to go to fitting a model. You can just get the mean for each level, and you can compare them to. I can compare each of them. EY5 minus Y0, EY4 minus Y0, right? You could pick a baseline value of the treatment and compare each of the other values to it. There's all kinds of things you can do that you would do naturally in less complicated settings where you're not worried about causal inference. So this is a Marshall structural model right here, because it assumes that as you change A, the mean of Y sub A, that causal counterfactual mean, will go up according to some model, like a linear model, right? That's what it is. So Marshall structural model really means that you're assuming that in our case, that the mean of counterfactual changes smoothly as they change the level of treatment. And smoothly can be as simple as a line, or it can be more complicated. It can be quadratic, etc. That's it. Doesn't mean it has to be linear. you can fit a marginal structural model that's quadratic. I could have a, plus a beta 2a squared if I wanted, et cetera. That's what it's as simple as that. It's just a different parameter. And now, of course, if I have two levels, that's just going to reduce to an average treatment effect. If A is just 0 or 1, of course, then beta 1 is going to be the same as the average treatment effect, and it's really back to what I'm going to get the same exact estimator I would have gotten in the last lecture. As A has more levels, that's no longer true. You're doing something more substantive, and then connecting 2 points. Now, at this point, if I'm not really worried about well, no, let's just go here. So anyway, here is the IPT estimate of beta in this case. So you have the model here, right? This is going to be like beta 0 plus beta 1a I. That would be an example. And then your this estimated equation is trying to solve this equation here with regard to the beta, right? So you're finding the betas for which that this sum will be equal to 0. And then again, you have this weight here. Now you have this h thing we have to worry about. And again, it can be any non-null function of a. So any function of a, but we'll talk about the specific ones that are used in practice. This is the most common choice of a, and you'll find justification for this in a second, because it has an analog in just least squares, which is you take the first derivative with respect to beta of this function, right? So, it's beta 0 plus beta 1a, then the first derivative with respect to beta, well, there's two betas, so there will be two first derivatives, partial derivatives. The first one, for the respect to beta 0, you'll just get, what, 1, and with respect to beta 1, you'll get a. So this derivative here is actually a vector of two numbers, 1 and a, in this case. And then times, again, some weight function. Again, we're going to see this just like we did in the stabilized weights. This is really to do stabilized weights. The reason this choice is appealing is that the standard regression software can be used, and it just means that you put in a regression of y on a and you add weights, and these weights are these right here. So if I calculate these weights, I can just do weighted regression. I don't have to write any new software or anything. Yay! And that's why these were originally took off, because they're very simple to implement. We haven't talked about what G star A is yet, but we will, but this we've talked about. That's like the propensity score. I get an estimated probability of treatment observed given W by, let's say, I have to do something besides just simple logistic regression, because A has more than two levels now, but that's not insurmountable. And then I get those weights, plug them in, and just do a weighted regression. Not of y on A and W, but just y on A. And it's going to reweight the data much like it did in the original simpler example where A only had two levels. So some brief intuition why it's similar to an analogous situation. Let's just assume we're not interested in causal inference, but just want a regression of a y on A. So this might be an example of our M in this case. And we're just trying to model that. One way I could do that is to find my loss function that I'm trying to minimize, a squared error. And so I define my estimate then as this right here, just minimizing the squared errors of the observed versus the predicted squared with respect to beta. And that has an analytic solution, right, if I do that. I mean, it has a mathematical solution. If that's my target, my optimization function, I can solve that. And when you solve it by setting the derivative with respect to beta equal to 0, right? That's how you find the minimum with respect to beta. That's the calculus problem there. And then solving for beta. And when you do so, this is what you get, right? That's where this thing comes from right here. So you can do it yourself if you care to. If you don't care to, you can take my word for it that this is the least squares estimating equations that you get from trying to solve the optimization problem. We are trying to minimize the mean squared error of the predicted minus the observed squared with respect to beta, that it ends up equivalent to solving this estimating equation right here. And you can see that looks very similar to what we looked at previously, except there were weights, right? The only difference between this and the previous one, the IPTW estimator for estimating the, not just the mean of y given A, but the mean of y sub A, is that you have these additional weights to re-rate the data. But you're still just regressing y and A with weights. And therefore, you end up getting this as your ultimate estimating equation that has these additional weights. So it's really equivalent to what we talked about previously, except for now you're not estimating just a couple of means and comparing them. You're estimating how those means change as a function of beta. So you've just replaced, you know, a model that allowed a separate mean for every confounder that was sort of, separate mean for every level of A that wasn't necessarily related to each other, didn't have to go up linear or not, into one where you're assuming a model. Much like you would in a standard regression, I could, if A had several levels, I could just estimate the mean of y given A is 0 by just taking the average of the outcome when A is 0 and the average, the outcome of A is 1, right? That would be equivalent to what we've done previously. Or I could fit a line through it and assume that, in fact, it goes up linearly and then do the least squares. Well, this is just adapting that least squares estimated equation for the goal of estimating the counterfactual mean by this inverse, this reweighting part here using these weights. And so while this one doesn't correct for confounding, this one does correct for confounding. This one's really not estimating the same, they're estimating two different parameters here. This one is a parameter which is ultimately estimating the mean of y sub A for different sub A's, for different levels of treatment. Okay, so how do you do this? Well, I've already alluded to it. You have to get this thing, again, just like you did in the previous one. There's no difference except for if it has multiple levels, you have to use something else besides. You can use trick logistic regression to get the probability as A is 0, A is 1, A is 2, etc. But one way to do it directly is multinomial logistic regression, which is a way of modeling categorical outcomes. It's a logistic, based on a logistic-like model. It would be asymptotically equivalent to just saying, picking, defining an A star, which is 1 if you're, let's say A is 1, and 0 if you're not A is 1, and you can fit that model and get a predicted probability A is 1. And then I can make it 1 if A is 2 and 0 if it's not 2, and get that one and get a predicted probability A is 2. And I could do that for every level and get predicted probabilities using logistic regression for every level. The one thing I lose is that doesn't guarantee in the end, when I sum all those probabilities together for the same W, I get 1. So you can normalize it to make sure that happens. And that's a way of using things like superlearning to do multinomial logistic regression. It's possible to just use a series of logistic regression fits to get multinomial. But when you have it available, you can do it directly. And the multinomial logistic regression is available in R and Stata, et cetera. The other data adaptive approach is, well, I just told you, there's a way to trick superlearner into doing it as well. Then once you fit that, you just assign the weights. Again, we haven't discussed what that G star is yet. It's going to be start out to be the same as it was in the previous lecture, just the probability, marginal probability of different levels of A. So either the probability A is 1 or the probability A is 2, et cetera, depending on what A you got, divided by this estimated propensity score. Probability of getting the treatment A you observed given W. In this reweighted population, just like previously, no longer, if you looked at the distribution of W and you treated these weights as representing the number of people that each observation represents in the target population, so you reweighted the data literally, you created copies, you should no longer see any relationship between A and W in your data. And there's little examples in these papers that show that. So once if I really literally treat it as if Those weights represent the number of copies of people each person represents, and reweight accordingly. I should see, when I look at the relationship in A and W, independence now. So I get rid of the association of A and W through this inverse weight, this reweighting. If W is sufficient, you have all unmeasured confounders. This is no different from the criteria from any of the estimators. Then that reweighted population will have no residual confounding. When I look at just the relationship now of Y on A, I don't have to consider W anymore. I've essentially pseudo-randomized now. Once I reweight, there is no relationship, so there is no confounding. And now I can just get the causal association like I would in a randomized trial by just comparing a regression of Y on A or just the mean of Y for different levels of A in that reweighted population. That's the intuition for why this works. Essentially, you're getting rid of the confounding by reweighting. And technically, I can do this by just standard software. I can just use linear regression and add weights. That's an easy operation in both Stata and R, and it will give me back an estimate using those weights, just as I showed you in the previous example. And it will use them in the right way. So if you use logistic regression with weights, it'll use it in the right way. And if you use linear regression with weights, any GLM, you'll be fine. Again, the choice of the numerator, when that model, that the M, this model, the M, A given B model is true, is the right model. I have the right, it's linear, truth linear, and I've chosen linear. It doesn't matter what I choose for G star A in terms of consistency. It's just efficiency. I can reduce the variability or increase it depending on how I choose that. So it doesn't affect that, at least the bias of the estimator. That goes away if I have the model is not correct. Then it actually really affects what the parameter is. But for now, assuming I got the model right, it does not affect the consistency. But it can affect efficiency. And so you want that same, might as well use that same G star we used in the previous lecture, which is just use the marginal probability that the A you observed is the A that you got. So when you take that ratio of weights between ratio of probabilities, G star A over G in A given W, you want to make sure of, G in A W, G star A, you want to make sure if that gets small, then this gets small. So it stabilizes the weight. And one way to do that is just to make G star A equal to P in A. That is, what's the empirical probability of that receiving that treatment in our population? You just can't count the proportion of people that got A as 0, proportion of people that got A as 1, etc. Okay, so we're going to assume it's correctly stabilized. We have the correctly specified. Here's our model. That's our M. We're going to choose this equal to the marginal probability of A, which I just discussed. And then this will be our stabilized weight. We can easily calculate using the regression and just the proportions, getting that ratio and plugging it in as a weight. And we already discussed this. Why use the G star that we did? Because if G of A given W is getting small, chances are also G of A is getting small. If it's just a group of people, just a treatment that's pretty uncommon, a level of treatment that's uncommon, then you don't want that to blow up the weights, and this will work. So that's basically it. Stabilization is really just made to avoid extreme weights. That's all it does. And again, the choice is arbitrary somewhat, but you would like it to minimize the variance if possible if you get the model right. And so this is an excellent choice. It's just the proportion. And this just shows you if I just have one person that is A is 6, well then P in A equals 6 is going to be small, right? Obviously, G in 6 given W is also going to be small. So I take the ratio, it won't be so small. That's all there is to it. Well, this weight, of course, could be tiny. When I stabilize it, it's not bad. And that's what you see right here. So. Now, one thing is, once you use these stabilized weights, you do have a weaker positivity assumption. You don't just have to have that probability not be super small or close to 0. You can make those weights so if, in fact, the denominator goes to 0, the numerator goes to 0. And that's okay. It will rely now on the MSM doing the extrapolation because you won't have all the data you need to do it non-parametrically. So you're using the MSM to say, okay, I may have very little data to look at the true counterfactual mean at this particular value of A because there's some W's that don't really have much experimentation in A, in that particular A, but it will extrapolate, right? So, because it can extrapolate. Once you have a model, you can extrapolate. Before it was silly to talk about extrapolation when it came to the effect, the counterfactual mean, because we only had 2 levels. But now we have many levels, let's say 10 levels is possible. That model itself can extrapolate. And that's actually might be useful for reducing the variability of how you report your results. If I have a situation where I have many treatment levels, and some I have more data and less data, if I can reduce this all just to 2 parameters, just a beta 0 and a beta 1, I gain a lot of efficiency, right? Because now I'm not getting a separate mean for each of 20 levels. I'm getting 2 parameters now, and 2 parameters as opposed to 20 parameters is a lot smaller number of parameters, which means I have more data to estimate them. I'm borrowing across all of these. So extrapolation and borrowing are one and the same. They imply the same thing. And borrowing could be a great idea if, in fact, sample size is relatively small and the MSM is actually a pretty good model for how the counterfactual mean goes up. Then fitting this as opposed to separate means gains a lot. And that extrapolation, if it's not wrong, becomes quite useful by gaining power. Here is the positivity assumption. You just need that the biggest value of this ratio among all those W's that are in your data, or in your data generating distribution, is less than infinity. So you just have to make G star A guarantees this, right? It means, though, that if this can be 0 if that's 0. It will then rely on some extrapolation, but it doesn't blow up anymore. So the stabilized weight, much like the previous example here, has a really beneficial effect, and it avoids a complete disaster. It avoids it completely exploding when you have weights that go very close to 0 or 0. As long as that stabilizing value in the numerator somehow tracks the denominator. So it gets very small when the other one gets small, and it gets 0 when the other one's 0. So, yeah. If you can see where this is really effective, and that is in the situation where I may have 20 possible treatments, but in my data I only got 15 of them. Some of them are missing. I still might want to fit this, and it will now extrapolate between some of the missing values. Sorry, I'm desperately blowing my nose. My nose is disgusting, so I'll go outside.
Here.
Oh, there it is. Thank you so much. Man, I have a terrible sinus infection. Don't get one of these. Be right back. So you can see, I was just saying, so in that situation, you can see the extrapolation helps you quite a bit. It may not be, it may not condemn your study, in fact, that you don't have every level of some ordered treatment, and you can still do a reasonable job extrapolating using this approach across values where there's simply nobody that got it. But, yeah.
If we had a slightly more complex MSM, like
a plus a squared, then we would just change the derivative.
Yep, exactly.
And tweak the G star.
I mean, and that will actually happen automatically by just running regression with a plus a squared. And it will, because the estimating equations for the linear regression already automatically use that estimating equation with the derivative of m with respect to beta. You don't have to do it automatically. It's done for you. But yeah, exactly. So that's a nice thing. It's very easy to implement because any model you put in there is fine, essentially. Yeah, I just talked about this. So, in situations where you don't even see some of the levels, it's still possible to get an estimate of that mean for every level. Of course, always caution has to be taken that if you're missing an intermediate level, it doesn't, of some ordered treatment value that goes from, let's say, 0 to 20, that somehow something drastically different didn't happen there. But if it didn't, this kind of extrapolation is reasonable, right? In case you don't know what I'm, picture what I'm talking about. If I have something like there's E hat Y A, and I have some values here, and then I may be missing some here. I might be missing some, but that's assuming that nothing crazy happens here and here is probably okay, right? If I'm extrapolating this way, and then it ends, and then I'm going over here, well, that's a problem, right? Extrapolation depends where you're doing it. If I'm extrapolating within the data, and I can see that extrapolation looks reasonable, that's fine. If I'm extrapolating outside the data like this, you're just counting on sheer luck. I mean, this is just making the point again, right? If I have a situation where one of the values has true probability 0, I just didn't get it, then you're basically out of luck. It won't work by getting a mean at every level. But again, that's an extrapolation in the right way, in the right context, isn't necessarily a terrible thing. And then again, this just makes the exact same point. So if the MSM is correctly specified and I'm extrapolating fine, let's say there's nobody got 6, then actually this works fine because the model works across the areas I don't have it. Here's a situation where it would fail miserably, because the truth is so much different than the projected fit. But, don't extrapolate beyond the data. In other words, just fit your marginal statistical model within the values you have. I mean, that's not, and don't use that marginal statistical model to project beyond the treatment levels that were observed in the data. That seems pretty clear. That's a common message for any kind of an analysis involving just simple association. So this is putting almost too fine a point on what's pretty obvious. Now, the last thing I'll say before stopping is one challenge you can give yourself, and one challenge that people who came up with this gave themselves and failed, is do something where you have a binary outcome and generate a data generating distribution that gives you some kind of linear or parametric curve for a marginal structural model. It's really hard to do. It seems like it would be so easy to do, come up with something that at the end would give me like a line for EYA or a line of the logit of that. But in fact, the people who published one of the major articles on this originally couldn't come up with a simulation where the true model followed a certain true marginal structural model, which just tells you that's a real issue reconciling these marginal structural models with some kind of possible data generating distribution. They're not consistent often, and it's hard to make them. So chances are you're not fitting the true model. Chances are it's really some projection of the true curve, whatever it happens to be, onto some simpler approximation. And that, once you think of it that way, all this discussion about how you choose G star A and stuff goes out, what we said so far no longer applies. It's not just a question of efficiency, it changes how you're weighting different parts of the fit to the curve, so it changes the parameter, essentially. Much like just weighted regression would change what you ultimately get in the limit, depending how I just weight different values of, let's say, A versus Y. There's no magic here in thinking about this. It's that once you're not fitting the truth, then how you weight certain parts of how a curve is going to be superimposed on the line will change where the line goes. That's all there is to it. And therefore, it doesn't become such a simple argument anymore. What you really are fitting, then, is this much more complicated parameter below. This is not something that just rolls off the tongue. This is the definition of a parameter, right? And it really, what it says is if I knew the true values of the counterfactuals, right? So I knew the true ones, I could fit all possible models to the true one, let's say least squares models, and what I want to end up with is the set of betas that gets closest to the true curve, right? So that's just like if I had a situation much like I drew before, where I have now these are the true values, E, Y, A, and I might have, so these are the true values. I want to fit the betas. I know it's not a perfect line, but I want to fit the betas such that it has the least residuals between the true counterfactuals and the line that I end up fitting. So I define the true parameters as beta 0 and beta 1 that minimize the squared error between a theoretical data set where I observe all the counterfactuals. You can think of it this way. If I had a data set that had where I knew what EYA was for every A, I could just regress that versus A. That's what I would do. That would give me my marginal structural model. And if the whatever I used wasn't true, it would give me a projection. It would give me some projection of that values onto that line. And so that's generally what you're doing, is what you think of it, is not so much fitting a true curve, but fitting a projection of some true curve onto the values. And just as I said before, it's just hard to come up with a data generating distribution that gives you a simple parametric marginal structural model when you're starting from scratch. And so it's likely these things are inconsistent with any data generating distribution, these models. This has caused a lot of debate in the literature about whether to treat it as the truth or not and whether this really matters. And it does matter, and it shouldn't be a debate. It's just a mathematical truth that the models are probably wrong, and we should think of it as projection. In that case, it's a perfectly fine parameter, but it really is this parameter, which is this projection. It's not just a simple, and I can't say it in a word. Yeah.
When do you know that in the projection case, when you're just trying to fit a line, which is the projection of the true E of Y onto a line, how do you know if that line is the best line or not? Like, are there...
Well, then you can come up with a problem of saying, I want the best projection, right?
Right.
And that is an optimization problem which has been solved.
Okay.
Yeah. Now, it turns out it's not going to be the same estimator we're talking about, but just using the estimator and going forward with it, saying, I realize it's not the truth, but it's some kind of projection, doesn't necessarily give you the best projection, but it's not a terrible thing to do. It's a reasonable thing to do. There are papers where they've solved the more complex problem of the best projection now that you think of it that way. Work that Mark has done with, I can't remember if it was Romain Neugenbauer, he has co-authors. It's part of it's the references at the beginning of this chapter. So it has been solved.
Mm-hmm.
I don't think it's an implemented algorithm, except in the LTMLE package it is. Not in the TMLE package. But for now, I'm really trying to give you, I don't think it's a terrible thing to fit a misspecified marginal structural model as just an approximation that's reasonable. I'm just trying to give you conceptually how to think about what the parameter really is from then. And this is not uncommon. Again, this is not specific to causal inference. Anytime you're fitting a parametric model, you're really fitting a projection of some unknown curve onto this, and that's the way it should be interpreted. And that's the way you should drive inference, is not assuming the model's right. That latter part has has more of a real impact. Like whether I use the maximum likelihood inference or I use something like Bootstrap will be different depending on whether I think I've really fitting the truth or a projection. If it's a projection, maximum likelihood inference that you would get back from a standard package doesn't work all the time, because it's assuming, when it gets its inference, that the model is correct. But like a non-parametric bootstrap or a sandwich-like estimator, much like based on the influence curve, still can work even if the model's wrong. But it's giving you inference for the projection, not for the truth now. So it's complicated. And there's no way getting around that. But generally, that's what we're doing with parametric models, is projections. And we should probably get our inference always using, in Stata, always use the robust. Doesn't hurt you. Use the robust command, because it's getting inference and not assuming that model is correct, but an approximation. Okay. Any other questions? I'm going to stop for today. The fact that it's probably generally more realistic to think of these marginal structural models not as the true model, but as some linear or some other approximation to the true curve. And just again, remind you, it's not complicated. It's just like the truth may look something like this, and you're fitting some kind of approximation, right? And that changes the way you think of deriving the estimates and the inference, for instance. And that's just generally true, not just true for causal inference problems, but also, as I mentioned, just for standard regression. How I get inference for fitting this line, if the curve is the truth, is different than if I think I'm actually fitting the true curve. I want to use something that doesn't rely on like homoscedasticity anymore, because that, by definition, will be violated in this approximation. So you want more non-parametric inference that really is just giving you the variability for this algorithm. You can think of it that way. I have an algorithm by which I fit the data. It's an estimator. I get a number back. And I don't want to, your safest bet is to get the variability of that algorithm and not assume that the underlying model, that line is actually based on an underlying true model. But as I said last time, when you give up thinking of it as the truth, the projection, you can think of it most easily, like I have up there, most in a visually, that you're really, you now are fitting. I have the true points here. Those might be the true EYAs, and here's A, and I'm fitting the best line to those points. So I can understand, when I say best, that's according to some loss function, like squared error or something like that, right? You can all probably understand and get a sense of what that looks like. What it looks like mathematically is this. That's how you define a projection. It's just the minimum over all possible betas of a line where the loss function is a squared error between the true counterfactual and the predicted given your working model. So you're trying to get an estimate of this working model, which is really just via the betas, so that line is as closest to the true curve as possible. Does everyone understand that? Or at least get some intuitive sense for it? And then now you can think of this G star A as just the amount of weight one puts on specific points. Like you can choose to weight different points on A differently. I could weight some higher than others and some lower than others, and that will give me a different curve, right? And I also discussed that a little bit last time. So once it's not the truth anymore, that however you define your weights, which will be a function of whether we have stabilized weights or unstabilized weights, will change really the definition of the parameter. It means in the limit, that will be a different projection because it will weight different points differently. So you don't think of them as different. Can no longer think of them as necessarily different estimators for the same parameter. They really define different parameters now. They're different weight functions. They'll in the limit go to a different thing, and so it really makes that choice of weight function a little bit more subjective at this point, and not something you're objectively doing for efficiency for a particular parameter, because it defines the parameter once the model is no longer true. That's also true with just standard regression. If I reweight things differently, then I get different lines as sample size grows. I think a good example of this, for any of those that had longitudinal data or repeated measures, and you had GE, you've been introduced to that, you have these choices of different working correlation matrices. And it turns out if the data is balanced or the model that you're fitting is true, as sample size grows, they'll all go to the same regression function. But if the sample size is not balanced and the model is not true, which is generally the case, that different ones, working correlations are really different parameters. They're going to weight the data differently, and that's going to result ultimately in different lines. So when they're no longer competing estimators for the same parameter. There's different parameters, and if you have independence working assumption for the correlation, that will be very different than if you have, for instance, exchangeable or compound symmetry, which will could reweight the data quite significantly. So this isn't a phenomenon that just speaks to this particular issue. It's just a general one. The weights don't really matter in terms of consistency when you have the right model, but when you don't have the right model, consistency is almost not really the issue anymore. They define different parameters. So that's all this says. It changes the parameter now because it just reweights that simple regression between the E, Y, A's versus the A's. So if some weight more than others on that curve, you're going to end up with different lines. And now the choices are, when you think of it, if you put the numerator, not that G star A, but you put it 1, it puts equal weight on all possible values. So it's not going to weight some values of A more than others. They'll all get equal weight. That may be maybe that's the line you want. If you use the stabilized weights, empirical portions with the subjects observed A put less weight on A's with few or no observations. So you're going to get reweighted. So if there are particular points on this curve, again, I can think of it just visually. And here's A, here's E, Y sub A, and I'm going to fit a line, right? If I weight these all equally, well, your line will probably look something like that. If I weight these ones higher down here because they're more common and these ones less, you're going to get something that's more like that, right? So it's not very complicated. It just means it really leaves it. It's not a statistical question anymore. It's a question of what you want, right? It's not a statistical question. I think of I have a particular parameter of interest, and I want the estimator that gives me the lowest mean squared error, right? Most reliable inference, that sort of thing. It's not that's not the question anymore. It's what parameter do you want when you choose the weight function when the model's not true. So that's a subtle difference, but it's important. And as I say, it permeates not just this discussion, but any discussion when you're doing regression. Here's just an example from Romain Norgenbauer's paper with Mark and others. Here's the true causal curve, so you can generate a simulation where the true marginal structural model looks like this. Okay, just arbitrarily chosen to give a curve of some kind. The working MSM will fit a line to that. Okay, so that's going to be our working model. It's the best fitting line to that curve, right? And that best will depend on how you weight. So in this case, here's the general target parameter now. It's going to be that projection, or really just the line that gets closest to the curve with respect to the weights. And we'll look at two options. One is to choose an option where the weight is just 1 for every point, and one is where it weights it more if it's a more common level of the treatment of the A. And you get two different curves in the limit, right? So if this is 1, they're all weighted equally, and you see that's a reasonable one. If it's this one, it could be that these points have a lot higher weight, but that must be the case here, right? Because they're getting much closer to those, and it's not as influenced by these points when the weight is the probability of A itself. So, again, it's just another example of how the weight function itself affects what the parameter is. and how it's no longer an objective choice like it would be. It's not an optimization problem anymore, where I really have one parameter of interest, and I'm trying to get the closest, the estimator that gives me the best performance.
Is
Yeah.
there any
Sure.
sort of guidance on how to select weights then? Or is this an instance where you would maybe want to do something more Bayesian and use prior information to inform your choice of weights? Or is it really a judgment call?
Judgment. I mean, it could be, there's two different parameters there, so to talk about relative performance becomes a little bit meaningless, but it could be one that the estimators from one of them, based on one weight, gives you huge variability. So you may just say, I'm going to choose a weight function, so I know it gives me different parameter, but the variance isn't so crazy, and it's subjective anyway, right? I mean, my guess, the unfortunate thing in terms of more of an art in that context. I think weighting by the proportion of people that actually get the level seems to make sense. But if you're most interested in extrapolating, for instance, that doesn't make sense, right? If I'm most interested in knowing what the mean would be for levels of A for which I don't have as much data, then I really don't want to overly weight the portion where I do have data, because it's going to fit that too closely and sacrifice the contributions from A's that don't get much, experimentation, or just don't get much data there. So yeah, I don't have a simple thing to say about it. Okay, the one great thing the marginal structural models allow you to do, quite without really learning anything new about the estimation procedure, with one small little twist, is they allow you to look at the stratified causal effect, right? So this is the mean of the counterfactual within strata defined by V, and V doesn't have to be discrete necessarily. It can be continuous as well. It could be age, it could be gender, and this is often really useful to look for things like interaction. Is the effect of this different among men and women? Is the effect different at different age groups? Particularly if V is a continuous variable, it's nice to have an approximate way of getting the effective interaction, which is defined by one parameter in this case, as opposed to many. If you're just getting the mean difference between, let's say, A is 1 and 0 within different levels of V, if V has many levels, that becomes something where it's going to suck your power away, because you're going to have very little information for every straight of V. But if you can assume a smooth model, and that's reasonable, then this is a nice way of getting these estimates, which is just more refined now. Now I'm not looking at the effect over the whole population, but within subpopulations, and I may think that the effect should be quite different, so that maybe that marginal effect becomes less interesting. Again, this has perfect parallels in things like 241, where you are just looking at associations and you have interactions, and so the odds ratio for one thing is different at levels of the other. What do you do? And you learn logistic regression that says, okay, add an interaction term there, and that allows me to account for it. Or if you're in a discrete setting, V is a discrete thing, you can just get an estimate for each level of V. It's just the same here, right? There's no new fundamental thing you're learning about this problem. It just happens to be it's not looking at interaction with regard to the mean of Y, it's the mean of Y sub A. Otherwise, it's the same issues. So, again, it just opens up other options in the estimator that don't really require any additional, any additional tweaks on the estimator. How would you implement this one? You just estimate this as you did before. So you still based on. By the way, V is a subset of W. So it's one of the confounders. Think of it that way. Or it could be, it doesn't have to be just one of them. You could have a model that has more than one. So the estimator still relies on this propensity score treatment mechanism thing, so you have to estimate it. Again, we talked about parametric approaches versus superlearner. or more data adaptive approaches. You get the predicted probability for each person, you use these to get the weights, and then you regress YNA according to MSM using those weights. Okay, I'm sorry, this is still just looking at models that don't include V. The only difference there is you include V. So for non-conditional MSMs, that means I don't have a V in there. I'm just looking at the marginal mean. Really, this is the mean in the whole population, how it changes as a function of interventions on A, as they change. It can be numerator in those weights can be any function of A, and this is a very common one we used, right? Because again, if you think of it no longer as the truth but a projection, for one, it makes sense to weight things higher if you have more data there. It's subjective, and it may be different depending on what you're trying to do. Also, if you think of it the true one, that stabilizes the weight, because if A is relatively, a certain level of A is relatively rare, that means the denominator, the G n of A given W, will also be a small number. So having a small number in the numerator means you're stabilizing those weights. You're not going to use big weights because those small numbers go together. For this, you can use a different numerator, and it should be any non-null function of A and V if you want a stabilized weight. Same issues apply to the weighting and whether this model is the truth versus a projection. So that doesn't change here, it's the same. And so as opposed to G star A, it's G star A V becomes the numerator in this weight function. So again, it's not fundamentally different from just having the A in there. You just have more variables in there, and now the stabilized weight allows you to include functions of V, which even tracks it closer, right? So now, if GA given W is really small, then GA of V tracks it probably more closely than G of A, right? Because V is a subset of W, and therefore it's probably further stabilizes than just putting G of A in there. And so here's the typical weight. If you implement this, and Stata has a version of this that's already implemented for you. So you put in your confounders, put in your treatment of interest, you put in your MSM, and it will default to this stabilized weight. This is the most commonly used one in the literature. It's the one recommended. And again, whether or not where this right here is an estimate of the probability A given V. So it means you need two now regressions. You need one regression where we're regressing A versus W, and then your regression of A versus V in order to make this weight. So you need two. And V, again, is just some subset of those W's, maybe one variable, maybe two. The positivity assumption here, again, it's always going to be this weight doesn't blow up, right? That's the positivity assumption. This weight doesn't blow up, right? And for that to be the case, that means this ratio, which is the weight, has to be less than infinity. And if one goes to zero, if that goes to zero, the other one has to go to zero, which of course prevents it from being infinity. So again, this is a sort of a technical but obvious point that we don't care about this going to zero for W's that we never see in our data. That's not relevant. And so it's only for those W's for which there's some probability we'll get a person that has this set of confounders. Again, just adding the V here. And so, and if it's, also, it doesn't mean that you have to have every level of V. I mean, V can be a continuous variable, right? So if it's continuous, really continuous age, you're not going to have every age in there. You're going to rely on some extrapolation, much like you would in any regression, where you have some variable you're regressing against that has, is in theory continuous, at least to some decimal place, and you don't have every possible value in a target population in any sample because at times are nearly impossible. So that implies that you're always going to be extrapolating at some level, but it depends on how much you're extrapolating, how much you worry about it. If I'm just extrapolating between 40.2 years of age and 40.7, that's my biggest extrapolation. Well, that's not much. I can probably rely on that function being smooth between those 2 points. If I'm extrapolating between 45 and 70, well, that's a huge extrapolation, and in that case, you're going to be very wary of any estimates in between those 2 points because there's no data. There's nothing magic about these statements here. They formalize that concept, but it's something that you shouldn't lose intuition over because it has no difference than a standard regression problem. I already talked about this. Why do they improve efficiency? Well, mainly because this thing will track more closely. This thing right here, this one, will track this one more closely than just G of A, right? Because V is a subset, so that's not necessarily, I could probably come up with a data generating distribution where that's not true, but typically, if I have just the marginal probability versus the probability within subgroups defined by V, which is a subset of W, it's more likely to be closer to that. And the closer it tracks, of course, the better stability you get. So you're avoiding, particularly if this gets small, you want this to get small, so the ratio doesn't get huge. The other nice thing is in the context where V is everything, there's no more confounders, so the other W's aren't related to A, then this weight just goes to 1, right? And then, of course, that's perfectly stable since there won't be any reweighting of the data. And that's really the typically most stable situation where you have the least variance. Went over that. Okay, so standard errors as they're, again, we've talked about different ways of getting inference for these kinds of estimators. One is that one that relies on the influence curve, which we've mentioned but haven't gone over in too much detail. We'll do more in the TMLE portion of the lecture, or the TMLE lecture. But you can approximate those influence curve-based inference by just using the standard errors returned from the regression program. I put in the weights, I run the regression. If I use robust option, for instance, in Stata, and there's equivalent version in R, it's this so-called sandwich estimator of the variance, but it really reduces to just getting the influence curve for the particular parameter and then using that to derive the variance. I mean, the way the sandwich estimator is typically presented in things like repeated measures class isn't in that context, but that can be derived that way. That's the more general way to derive it is, I have this estimator, can I write it as some mean of IID random variables plus some second order stuff that I can ignore as sample size gets large. And if I can do that, all I need is the variance of that influence curve to get the standard error. And that's the way it's essentially derived behind the scenes. I mean, again, it can be derived in a different way, but it converges to the same thing. So if you use the robust option after you run this with weights, you get a standard error that will be, it will be conservative if you get the estimate of the propensity score right. If you don't get it right, all bets are off. You don't know what it's getting exactly. It still relies on getting that right. And, if you can't get consistent inference that gives you exactly the right confidence nominal rate, 95%, of the times your confidence interval contains the truth, for instance, you want one that's at least 95% or greater. That's the rule we go by in statistics. If you can't get it, you don't err on the side of anti-conservativeness. You err on the side of conservative. So at least you're getting something that is as big as it should be, if not too big, right? You don't want it smaller. That's a tradition. It seems to me a fairly logical choice. It isn't necessarily an objective choice, but given that that's what people expect, then that's what we go for confidence intervals. And given that, the literature is just littered with false positives, probably not a bad idea to be conservative. In fact, it's a very good idea. But the truth is, they can be too big. I mean, in other words, you can get 95% in name 95% confidence intervals that are really 98% confidence intervals. So you actually have more information than you're reporting about the parameter estimate. I mean, that's the downside, obviously, of a conservative confidence interval. You really like to have something you can guarantee is 95%. That's often hard to do, but that would be the best. If, in fact, the weights are used in machine learning, you don't know the truth, and you're fitting something that your hope with sample size at least grows would converge to the truth, then, of course, you're getting a biased estimate of the propensity score, and that means that your inference, the standard errors based on the influence curve, will also be wrong. It's a lot of simulation work has been done on these, and it shows contexts where they do better or worse. There's nothing universal to say about that, but you certainly do better if you don't know the truth by fitting something data adaptive that at least you have some hope of going to the truth rather than a fixed parametric model. As sample size grows, doesn't guarantee it for a small sample size that's the best thing to do, and there's no real good theory to tell you what to do precisely, which is why you really want your data adaptive procedure to make a model that's as big as the data will support, right? The bigger, the less biased probably. And you don't want it to be too overfit because the variance blows up. So it's a good idea to do superlinear, but once you do it, and you do it by necessity, it's not like, I'm just going to do a parametric model because then I'll be conservative. No, you'll be wrong if the parametric model's wrong. So it's a good thing to use data adaptive techniques, but the theory doesn't, the theory no longer carries through guaranteeing that you have proper inference. So what's the obvious alternative? Well, we talked about the bootstrap here. And in many contexts where some analytic version of getting the standard error or maximum likelihood version fails, the bootstrap will still be consistent. It's really, it's really just an estimator of the standard error for some algorithm where you repeat that algorithm on a new experiment, precisely like the experiment you did to generate the original estimate, and you look at the variability of those estimates across those experiments. Except in this case, you're mimicking actually sampling from the target population by sampling from your data. And when that mimics what you would do by having a new experiment, it works well. When it, for some reason, a bootstrap sample is very different in the performance than a non-bootstrap sample, than an actual sample, then it breaks down. And one place it can break down is any procedures that are very sensitive to ties. So if I have anything that I do where there's ties in the data, like both, that means both, I have two rows that have exactly the same values of the outcome, treatment, and covariates, and that has a big impact on the result of that procedure, the bootstrap fails, right? Because there's going to be ties. So, there's formal theory that tells you when it will do well and not do well. It's the same theory that applies to inference via the influence curve, and then it has to be asymptotically linear, blah, 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 blah. But from like a practical standpoint, to anticipate when it will fail, if you know ties are going to have a big impact, then you have to worry about with the bootstrap how it's going to perform. And it doesn't just it's not like just a trivial thing. It can do terribly. It can really do relatively poorly. Can you think of situations where ties have a big impact on the estimator, having them versus not having them? I mean, one would be things like with clustering, right? You're looking at clustering, and I'm somehow you have a clustering algorithm, and I am going to resample, and I'm clustering the objects, not the variables, right? Because the clustering can do both. If I'm randomly resampling, and now I have ties, that's going to have a huge impact in clustering, because those things are going to tightly cluster together exactly the same, right? So you get a very different looking set of clusterings of repeated bootstrap samples than you would if you actually had an experiment on the data, because it's so dependent on the minimum distances between observations that won't work in that context. That's just one context. If you have any procedure where the clustering of observations results in an estimate, then the bootstrap probably is not gonna work there, the non-parametric bootstrap. Anything that involves cross-validation, where you're have a training set and you're predicting on a validation set, unless you're structuring the cross-validation to avoid ties being in the same validation sample, you also have a problem, because it's going to it's gonna choose the model that does a really good job using the same observations to predict themselves. You can imagine things like nearest neighbor procedures, which just try to find a neighborhood around each observation to find by their W's and A to predict the outcome. Well, if you have ties, you can do a great job by just picking the closest one, right? And that's very different than going out and getting a new sample. So if you do something where your validation sample may look great in terms of how well it predicts, at least for some of the observations, when in fact it would never do that good in the original sample, and you end up overfitting. You end up choosing bandwidths, that is the neighborhoods that are too small in the bootstrap relative that you did in the actual data. So there's places where it fails and doesn't work well. And there's ways sometimes to fix how it fails, and it's ongoing research in our group how to modify the bootstrap. But at this point, if you're using data adaptive things like superlearner, you can't blindly use it within a bootstrap typically, because it in itself involves cross-validation. If this is the case, you win by using the bootstrap. If you have a parametric model, this is not an issue, right? You're not using cross-validation to choose it. It's a preset model. And then the bootstrap is a more probably accurate way to give confidence intervals than it would be using the influence curve-based method. What's the downside of using the parametric model? It's just not right. So you're just getting a confidence interval around a biased estimate. If it's estimated using machine learning, no theory that the bootstrap will necessarily work in that case. So that's the downside. What's the upside? You may not be as biased, exactly. So there's, it's the no free lunch general rule of statistics that always comes back to bite you. So the key points, it relies on a consistent estimate of this treatment mechanism, much like the G-comp procedure. This relied on consistent estimate of the mean of Y given A and W. There are times where we know this well, like a randomized trial. So a thing based on this estimator where I know the true model, and therefore I can fit something that contains the truth, I can guarantee consistency. So there's times where that difference matters. We talked about the challenges of estimating this data adaptively, the treatment mechanism, in that is geared towards doing a great job predicting treatment, and there are situations where that can do a terrible job estimating the parameter. For instance, choosing things that are called instrumental variables, variables related to treatment that are not related to the outcome independently. So you have to be smart in your covariate selection here, and again, I think these situations can be often avoided, so it may be a fatal flaw if things are done with not a lot of thought and given how you choose them, but in practice, maybe for many situations, that's not so bad. And in the end, it's probably better, for instance, to use the bootstrap, because if you have a parametric model, if you don't, you just have to be wary of what you get. And always look at the bootstrap distribution. The bootstrap just gives you back 1,000 estimates. You get a histogram of them, and sometimes you can diagnose problems by just looking at that. It doesn't look normal, for one. It's highly skewed. That's going to tell you, there's problems. It could be that the bootstrap is working and the sampling distribution isn't normal, or the bootstrap is not working. I can tell you either of those things. Both of them are a problem.